Hello and welcome to my presentation at this summit. My name is Barbara Giegel and I'm a PhD student at Graz University of Technology. Today I will present you our verification tool, which has the name Coco. So I've divided this presentation into 3 parts. First of all, I will give a short introduction on the topic. Then I will introduce our verification tool. And in the third part, I will show you how we can use it to design a secure CPU. So this work is joint work by multiple authors from Graz University of Technology. Let's start with the first part, the introduction. So Coco is a tool which helps to verify masked software implementations. You construct a masked implementation whenever you want to counteract side-channel attacks. Side-channel attacks are attacks where an attacker exploits side-channel information. This is basically just information leaked by a device unintentionally when it does computations. For example, a CPU which executes AES leaks side-channel information in many ways. For example, the execution time tells you how long the encryption takes. Or what is important for us is the power consumption. Also electromagnetic radiation, which is similar to the power consumption, but also things like sound, photon emission, and temperature are side-channel information. We want to focus on power analysis attacks. This is a specific kind of side-channel attacks in which an attacker exploits a cryptographic device which does a certain computation, for example, AES. And the attacker wants to steal a secret key from the cryptographic device while it does the computation. For that purpose, the attacker uses an oscilloscope, which records the power information from the device while it does the computation. And this power consumption is delivered back to the attacker in a so-called power trace. You can see it here in the image. Now everything the attacker has to do is to make a connection from the power trace to the secret key. And this connection can be made because the power consumption depends on 2 things. First of all, which instructions are executed by the CPU. What is done. And second, which data is being processed by the instructions, so which data is involved. And countermeasures aim at breaking this dependency between the power consumption and the data. And a very prominent example of a countermeasure is called masking. Masking is essentially a secret sharing technique where one splits a secret S up into 2 parts, a random mask M and a masked value VM. M is random, so VM appears also to be random. In the case of Boolean masking, which we consider with our verification approach, we can share or establish the sharing by computing the XOR between the masked value and the mask. And the good thing is, the cryptographic algorithm does not operate on the secret data directly anymore, but rather on the shares. And since they are random, the power consumption will not reveal anything about the secret data anymore. Constructing such masked implementations of cryptographic algorithms is not easy. And therefore, there's a need to do verification of them. So to prove that they are correct and that no secret shares are combined during the computation. However, in the verification of masked software implementations, there exists something which is called this hardware-software gap. We have a piece of masked hardware on the one hand, for example, a RISC-V assembly implementation, and on the other hand, we have hardware. In our case, this was the RISC-V EBX CPU. And the hardware now executes the software. If we do software verification, we can prove that the software is secure. So this is very nice, and there are many methods which work really good in literature. However, all these methods neglect that we have a piece of hardware here, and that this hardware is not necessarily secure, and that it will combine shares in a way which is invisible to the programmer, and therefore not visible in the software. So what we have to do is we have to co-verify software running on hardware. With our approach, which is called Coco, we provide a method to do so. So Coco verifies that the execution of a mask assembly implementation is secure on a certain processor. As you can see here, we chose to work with the processor's netlist because we wanted to eliminate effects which are introduced by the synthesis and optimization process. And we want to work with the netlist which is as close as possible to the final ASIC tape-out. And verification basically involves to check that at no point in the netlist 2 or more shares are combined. And what is the hard part about it is how can we bring the software into the game? So how can we bring hardware and software together? And we do that by creating an execution trace of the software before we start the verification. This execution trace kind of illustrates the software as a sequence of control signals, which leverage the data flow throughout the CPU. And therefore, we call our verification approach execution aware. Therefore, it's also very important that the software has a constant control flow. So let's sketch the control flow of Coco. So we start with a masked software implementation written in RISC-V assembly. And this program should be executed by the EBX Core, which we create a netlist of using the YOSYS synthesis tool. The first thing we do is to create the execution trace by using a simulator. In our case, this was Verilator. Once we have the execution trace, we label the circuit's inputs, so in our case, the registers and memory locations, to give the verification method a notion of in which register is a secret share, or in which register is a random value, or in which memory location is a random value, and which registers are unimportant and not relevant for the verification. In the third part, the actual verification starts, and it has 3 inputs. First of all, the labeling. Second, the execution trace, which represents the software. And third, the hardware, so the EBX Core. The verification process has as output either yes, this is secure, or no, it's not secure, and you should have a look at cycle 8 and gate rec read, because there is a leak, and it comes to a combination of secret shares, which reveals something about the secret. Okay, let's have a closer look at this last part. So we start with the labeling of the registers, and these are kind of our initial registers. They have a label assigned by us. Then we propagate this label throughout the netlist of the processor until we reach the same labels again, because then we have verified one cycle. We repeat that for as many cycles as needed. What does propagation now mean? Propagation means that for each gate or register, we compute a correlation set, which tells us if the gate correlates with a share, with a mask, with a combination of both, or does not correlate with anything interesting. And correlation sets can be stable or transient. Stable means that they capture the circuit's behavior once the circuit has stabilized. Transient means that we can also cover something like glitches. But let's look at that in a small example. So here we have a small circuit, an AND gate with 2 inputs, A and B. A comes out of combinatorial logic, while B comes out of a register. Here we see also that we have an execution trace telling us the values of the control signal B. And now we want to compute the stable and transient correlation sets. So in cycle N, the stable correlation sets of X so we are interested in the sets of X, are simply the one from A, since B is 1, and the output of X will be A. However, in the next step, B switches to 0. So the stable correlation set of X will be a constant, since it does not correlate with A anymore, because A can pass through the AND gate. However, the transient correlation set of A is taking over, because there might be still a small time frame in cycle n+1 where we can read the value of A on the gate output, because B might actually glitch. In the next cycle, we see that B still is 0, so it's not possible that we have a glitch here anywhere, and the output of X will be stable 1, no matter what A was. Therefore, we can also say that in the transient case, X will correlate to a constant. So now you've seen how our verification tool works. Now I want to show you how we can design a processor with this approach, which allows the secure and leakage-free execution of mask software implementations. We selected the EBX Core as our target processor. So the EBX Core is a RISC-V core. You can see it here in this nice image, which has 32-bit registers and a two-stage pipeline. And why did we select exactly this core? Because it is small, has a simple microarchitecture, so no caches, for example, but contains still the most important components which are used in every other core. For example, the register file. Every core has a register file, and if we design some secure components for the register file, you can easily map it for the larger core. But also there has been some attention towards the EBX Core. For example, it's part of the PARP platform and also Google's OpenTitan project. So what we wanted to do now is to use Coco and verify the EBX Core with it. Our workflow was as follows. So first of all, we constructed a set of test programs, which were algorithmically correct masked software implementations. Then we execute them with EBX to get the execution trace and put that into the Coco verification. Then Coco usually reported a lot of problems, and we fixed these problems either in software or in hardware and just repeat the whole process again. So it was an iterative design process, and then until we arrived finally at a secure EBX Core. And the first kind or category of problems which were reported by Coco were things already known in literature. And we put that into software constraints, so we changed our test programs. However, the second problems were not so easy to fix in software, and some of them even not possible. So we decided to change the hardware. And in the EBX Core, we identified 3 sources of leakage. However, in a real analysis, you would also have to focus on how to build a secure data memory. I will not cover it in these presentations. If you're interested, you can look that up in our paper. So let's start with the first leakage source, the register file. So the register file originally looks like this. We have a multiplexer tree for reading and a multiplexer before each register for writing data to the registers. We identify 3 problems here. First of all, wires in the multiplexer tree can switch due to the addressing mechanism here. So if the bit 5 of the read address switches from 1 to 0, we read in one cycle first x1, second x2, and if they are shares, we have a leak. But also the address might be glitchy, and there are even unintended reads in the EBX Core, which means that, for example, the instruction add immediate x1 5 will read register x1 and also x5, even though we do not need it, just because the decoder directly interprets the instructions bits and puts it as a read signal into the register file. How do we solve that? We introduce register gating. So register gating, first of all, stabilizes the read address by using a one-hot encoded fashion and storing that into a register. So each bit in this register is the gate bit for the general purpose register here. And only if the gate bit is 1, we can actually read the value. And the same thing we do for the write mechanism. We gate the data which should be written to the new register. Okay, the second source of leakage was the computation unit. So the EBX has computation units, and the problem is that they are always active. For example, this multiplication instruction will also cause an XOR to appear in the arithmetic logic unit. And this is problematic with a special kind of masking schemes where you put the bits of a share into different registers. Therefore, we also use a simple gate mechanism here, which is actually pretty much what we did for the register file, an AND gate before the input of the computation unit connected with an enable bit. And the third source of leakage are the Loadstore operations, to be precise, the misaligned memory accesses, because misaligned memory accesses use a buffer register internally to accumulate the memory word which should be read. And this is an internal register in the Loadstore unit. And if this internal register contains a secret share and is overwritten by its counterpart, we have a leak. So thankfully, the misaligned memory accesses take quite some time, and we can just use the last cycle of this time frame to clear this register. So there's no override anymore. Okay, in the quite a huge part of our work was also to evaluate this design proposals. So first we evaluated the area overhead, and we came to the conclusion that the proposed hardware fixes introduce an area overhead of 2.2 kilogate equivalent, which is about 10% of the whole chip area. Then we also constructed a set of real test programs. You can see here, this is only a very small set, that we have different masking techniques like DOM. We have here a Trujillo AND gate, which takes, in the transient case, about 19 seconds to be verified, but also this broken implementation. Broken means that the implementation does not align to the software constraints. The largest test case we have is this AES box, which has almost 2,000 cycles, and it takes 5 hours to be verified completely. But we have also higher order test cases. So also these are feasible in time. So it takes about 1.3 hours for this Kerchak S-Box implementation for a second order case. And in the third order case, we also have this DOM implementation, which takes almost 3 minutes. Okay, so of course, we also did a practical evaluation of all of this. We put our design onto an FPGA board and did the evaluation. So we compared in this evaluation the original register file without any security fixes to the secure register file with the gating. And we observed the power consumption of this register file while a first order DOM Kerchak S-Box is executed. And we can see that for the original register file, we see at several points significant peaks in the t-test value. However, in the secure register file, we see that there's no peak above the significance border. So we are pretty confident that our proposed fixes are really secure. And this actually leads me to the end of my presentations. Here you can see some references I've used for the presentation. And so I hope you have enjoyed the presentation. I've introduced to you our verification tool, Coco, and how we can use it to secure the RISC-V EBX Core. Thank you very much for watching my presentation.